this course will be the final course on declarative algorithms and declarative programming. So, and I'm going to again explain why it's a good idea to write most of your program this way and show you again how powerful it can be. So I'll start with giving an overview of all the different declarative paradigms we see. And in fact, there's a lot of them. And I'll make a table, I'll show you. And different programming languages support some of these. So you can actually download these languages and try them out. It's not just Oz. Languages like Haskell or Prolog or even cloud tools like MapReduce will support some of these paradigms. Then I'll give you a definition of what it really is, okay? Declarative programming, especially declarative concurrency, since the concurrency is very important. And then in the second part, I will show you more advanced techniques of making algorithms. So you have already taken a course on algorithms and data structures. But I'm going to show you stuff here that you have not seen in the other course. That in the other course, the algorithms are all done in an eager, simple way. But now I'll show you more sophisticated techniques using all the concepts we've seen: single assignment, concurrency, data flow, and the lazy evaluation. With that, we can make even more smarter and more efficient declarative algorithms. So that I'm going to show you in the second part of the course. All of this is in the book. So in different sections, 452, 414, 344, 458. So I really encourage you to look at that. It's not just the lecture. This part, these things are also explained in the book in different sections, and I think it will help you understand. So let me now explain declarative paradigms. We've seen a bunch of them. And in order to understand all these different paradigms, so we start with functional programming, sequential, we add concurrency and data flow variables, or the single assignment variables, then we add lazy execution. To understand all these different models, I will explain, give you a good intuition by talking about the 3 special moments in the lifetime of a variable. And this will help you understand. When you create a new variable, this variable has a lifetime. It's created, eventually it's bound to a value, and then it's like a mature variable. But there's actually 3 moments that are special. The first moment is the creation of the variable. When you define the variable, when you do a declare or local, you create a variable. Once you create it, you can put it inside data structures, you can pass as arguments, it's already there. And the second one is specifying the function that will give its value. The function that will give its value. If I do x, for example, so this little x is a variable in memory, yeah? It's not an identifier. And I can do x is equal to f of y. But here I specify the function, it's f. But I don't evaluate it yet. I just say which function it is. I just define it. And the third moment is when I actually evaluate that function. So these are separate moments. And in many programming languages, these moments are done together. But it's interesting to see what happens when you separate them. And this gives us a bunch of different possibilities. Okay? So let me make a table of paradigms and how different languages do that. So this table is actually in the book on page 286, but I will give you some more information on the board. I will make it a little bit more clear now. So there's actually six parts in this table. So in this axis, I'm going to say either I do eager execution or lazy. So lazy is with weight needed. And on the horizontal, I will do pure sequential with values. So values are constants. So this is just a sequential language with values. So this area is what you have seen in courses on algorithm design. So the usual courses, usual programming languages like Java, they sit here. Now they also have concurrency, but the concurrency is not done in a declarative way. So you have to say algorithm design courses. So this is something like standard functional programming. What's usually called strict functional programming. Strict is very similar concept to eager. Okay? And typical languages here are Scheme and ML, which have very active communities. So these languages are very lively, and have many people using them. But they are sitting there. Now we can have also sequential with what I call data flow variables. So these are the single line assignment variables. So still sequential language, no threads, but data flow variables. So this actually is basically strict functional programming with data flow. So what is that useful for? Actually, this lets you do interesting things like tail recursive list functions. So in sequential with values, the append is not going to be tail recursive, because when you create a list, a const pair, they have to be all values in there. That means you can only create it after the recursive call. But if you have data flow variables, you can create the list, the output, before the recursive call. So this gives you tail recursive list. So it's already an advantage here. So what language is doing that? There's actually a language that does part of that. There's no language that completely does this. Let me tell you one language that does part of this. This is Prolog, which is a logic programming language, but not full Prolog, only deterministic subset. Prolog has a search. If you see the course of constraint programming, or if you followed my logic course, you see Prolog is actually doing deduction, but it's actually doing search. But if you don't do search, if you write just deterministic programs in Prolog that don't need to search the axioms, then it's doing this. Because Prolog has these logical variables that can be unbound. Okay? So full Prolog has also search. In addition, which I'm not talking about, search is another concept, a powerful concept, which I'm not presenting here, but which is also very useful. And in fact, modern languages generalizing that, this gives constraint programming. If you do Prolog in a smart way, with more powerful relations, you get constraint programming. And in fact, this is a very powerful and useful paradigm. Constraint programming is actually used a lot. And in this department, we have big expertise in constraint programming. Put this, I don't want to block the screen. So if you're interested in that, if you're interested in really powerful declarative programming, you should take the course on constraint, especially since you have the advantage that in this department, in UCL, we have some world experts on constraint programming who do research and know this very well. People like Yves de Ville, Pierre Schoos, and Siegfried Naesen are very experts in this. So this actually is, this constraint program is actually going in this direction, but adding very powerful search techniques. Okay, so that's here. Now let's go to the third one. We have concurrent language with data flow variables. So this is our deterministic data flow that we talked about a lot in the previous course. Deterministic data flow. And I also called this concurrency for dummies, because you can add threads wherever you want. This is a very nice concurrent paradigm. In fact, this one is actually very well used. All the cloud tools, the big data analytics tools, are actually using this one. I write MapReduce here, which is like the grandfather of all the cloud tools, which was invented by some people in Google at the end of the 1990s. But all the modern cloud tools, like Apache Flink, or the graph computation tools, they're all using this model. They're all concurrent, and they all have data flow variables. Okay? So now this is all the eagers. Now let's look at the lazy guys here. So if we take if we add lazy evaluation in a sequential language, then we have what's called lazy. It's sometimes called non-strict functional programming. There's a very influential, nice language using this called Haskell. So if you're intrigued by that, Haskell actually has a huge community. A lot of these people are mathematicians. They're using category theory, for example. So Haskell is, in some sense, a very powerful language using sequential lazy. But it's not concurrent. Well, it does have concurrency, but it doesn't have declarative concurrency. So you can say that the laziness in Haskell is actually doing co-routining, which I'll explain in a minute. So co-routining is almost like concurrency, but there's no scheduler. The threads are giving control explicitly to other threads. So let me say a few words about co-routining. Co-routines. So if I have a thread 1 and a thread 2, so the execution is going from left to right here. So thread 1 is executing, and then it actually gives control to the other thread explicitly. So there's an operation that's often called yield. So it gives control to the other thread. Then the other thread executes, and the other thread does a yield operation, and it goes back to the first one. Okay? So the threads are giving control. This is by the programmer, by the application is doing this. There's no scheduler. It's the application is deciding when to give control. So you see, this gives another responsibility to the programmer. This is sometimes called non-preemptive concurrency. Okay, so there's no scheduler. So it's deterministic. It's not non-deterministic. Yeah? Scheduler adds non-determinism. Okay, so it's actually deterministic. Because the programmer decides when to yield. It's not the scheduler deciding using some magic hardware clocks or something. Yeah? So this is non-preemptive concurrency. So laziness in a language like Haskell is actually switching back and forth between the function computing a value and the function needing the value. So when I need the value, I do coroutining. I go to the other one, and the first one stops. Okay? So laziness in Haskell is a form of coroutining. So the advantage of that is that it's deterministic. Also, it has, of course, disadvantages. You can't really write some programs in that. Let me now show another one, this one, the concurrent lazy model. So this is the model which we've called lazy deterministic data flow. In this model, you can write a bounded buffer. A bounded buffer, which we saw 2 weeks ago, is actually combining lazy and concurrency, because the producer and the consumer are not synchronized, really. So in the bounded buffer, the producer can get ahead of the consumer. Okay? So if I have a producer and a consumer, here's the bounded buffer, consumer, the producer can get ahead. That means it can do more values even if the consumer has not asked for them. So that's a form of concurrency. Concurrency, the threads are independent. So the consumer can get ahead of the consumer. This is not possible in a language like Haskell. In Haskell, you cannot write a bounded buffer because the producer and consumer are executing in lockstep. You can say here. That means the consumer needs a value, then control switches to the producer. This could be the consumer, this could be the producer, Fred. Consumer needs a value, then the producer calculates. And then the consumer continues, it needs another value, it asks again. So control is switching back and forth in this kind of a language. Whereas in this language, lazy deterministic data flow, both producer and consumer are concurrent. That means the producer can get ahead. Okay, so that's an advantage and a disadvantage. So the advantage is you can build a bounded buffer and it makes execution go faster. The disadvantage is maybe the producer is doing too much computation. The values that it computes here, it's not absolutely sure the consumer will ask for them. In a language like Haskell, you're doing really the absolute minimum amount of computation. So that's a power here. But the disadvantage is that maybe you want to get ahead a little bit to go faster, because then the consumer can immediately get the value. But sometimes the producer will go too far ahead. Maybe it will compute things you never need. Okay? So, but in practice, it's not usually a problem, because there's a pipeline. But it's a risk. Maybe one of these values takes huge amount of computation, but the consumer never asks for it. Well, this model will pay that price, whereas Haskell will not pay that price. Okay? So there's actually a place for both of these models. Okay, here the middle one. So this is what I would call lazy functional programming with data flow variables. So the laziness without with data flow variables, this model is actually not so much used. It's actually maybe less useful model than the others. Okay, the other 5 are all very useful. Here also you can do things like lazy quicksort in the final one here. So this gives you some notion of all of the space declarative paradigms. And you can see that many of them are supported by programming languages. So in this course, it's nice to see all of them. Okay? And in fact, the lazy deterministic data flow, some of the cloud tools are also using laziness. Okay? They're doing on-demand computation. So this cloud area is actually moving down here. So if you take like a course in cloud computing, you'll see that the models, the paradigms that they use is actually sitting here. Okay? Even though the course doesn't talk about it, it will help you understand what these executions are doing. Okay? All of these models are declarative. So that's the big advantage. They don't have mutable state. Okay? They don't use mutable state, they're all declarative. And the advantage of that, so there's many advantages of declarative. The advantage of that is that there's no race conditions in the concurrent programming. You don't have to worry about blocking. It's very easy to parallelize. Also, testing is very easy. You can test the different parts independently because they don't have a history. Okay? A language with an object-oriented language like Java, the objects have mutable attributes inside, so the value inside an object depends on the history, all the previous calls. This makes testing very hard in a language with state. This is not the case here. All these languages have programs that are easy to test. They're easy to build. You can build them layer by layer. You can build a function, test it separately from the other ones, and use it forevermore and other places. So this is a huge advantage. There's also advantage in distributed programming. When you start building distributed programs, it's even much harder because you have failure, possible failure of nodes. The strength of this model is even bigger. So one of the lessons of this course is that when you start building systems, try to stay in this model. And it's not so limiting. You can see the model has a lot of possibilities. Of course, you can't always stay in here. You do need the other state, mutable state, or ports, as we will see. You do need the other ones, especially when you interact with the real world. You can't always stay in there. So sometimes you need to leave this model. You need more. It's essentially when you have real interaction with the real world that you have to leave the model. When you have timing, user interface, a lot of events coming from outside, then you sometimes have to leave this model. Okay? But most of the code, that's actually only a small part of the code. If you write big applications, you will see that you can stay a lot in here. Okay? So that's kind of a summary of all the different declarative paradigms. Maybe there's more. I have no proof that this is everything, but it's what we understand today. Okay? So let me now go to a little bit more theoretical part of the course. Let me do a little bit of theory. So this course is mostly practical, but there's a little bit of theory, and I want to give you a more precise definition. I want to say, what is it exactly? I want to give a more formal definition of this. Here I tell you these are all declarative, they have no race conditions, and so on. But what does it actually mean? What is it, actually? So in the previous course, we saw a formal definition. In the previous course, we saw lambda calculus, and we saw the Church-Rosser theorem, which says that all reduction orders give the same result up to variable renaming. All reduction, that means all execution orders give the same result. Up to variable renaming, but that's essentially the same. Okay? This is a form of determinism. This is also called confluence. People talk about confluence. This is coming from Latin and Greek. Confluence, fluence, so flowing together. So basically the executions, even if you go different reduction orders, the result is the same. So it flows together. This is called confluence. Okay? So you can look it up, Wikipedia, if you want more detail. So this is the foundation of the advantages of declarative. So how does this work in our models here? because Church-Rosser actually says that you start with an expression in lambda, you have an initial expression, and you do reductions until you have a final one that cannot be reduced to more, so the program is done. And this is the result. So Church-Rosser, so here you have steps, reduction steps. And this is lambda calculus expression. So the lambda calculus only has functions. It only has function definition application. So I'm not going to go over this again. You saw actually the lambda calculus in the previous course. So you start with an initial expression and you do reductions until you end with the result. So you're only doing one computation here. So there's no interaction with the real world here. And so it's just one computation. But in our declarative models, we actually have more than that. Okay? We do more than this. So how does it work? So let me show you how we go beyond. So we're actually using Church-Rosser as a building block. We're putting it together, but we're using it in a more general way. Okay, so let me just say, so we're going beyond Church-Rosser in our declarative models, in our declarative paradigms. So how do we go beyond? Well, we go beyond in several ways. One way we go beyond is that we have partial termination. We can have an agent, which we give a stream to this agent. 1, 2, 3. For example, it computes the squares. 1, 4, 9. So in Church-Rosser, we have an initial expression and a final one, and it's done. But in this agent, it's never done. Okay? So it's never actually done. Completely done. Because we can extend the stream, 1, 2, 3, 4. Here we have 1, 4, 9, 16. Okay, so here we have a first computation. 1, 2, 3 gives 1, 4, 9. And Church-Rosser will apply here. But it's not finished. We can extend the input stream. 1, 2, 3, 4. We can add the 4. So we have extended it. So all of a sudden, it's not done yet, done anymore. We have new computation, and we get 1, 4, 9, 16. And we can keep extending. We can add another input. So you can see that Church-Rosser doesn't really apply, because Church-Rosser has a beginning and an end. You start with the expression, and you compute, and it's done. It's over. But here, you start with an expression, and it's done. But it's not done, because you can keep extending it. Okay? So the way you can actually still fit Church-Rosser in there by saying this is a partial termination. It's terminated, but only temporarily. So 1, 2, 3 gives 1, 4, 9, it's done. And if we don't give any more input, then we don't get any more output. So it's done. And in this case, Church-Rosser applies. From 1, 2, 3, 1, 4, 9, we have perfect determinism confluence. But then we can add more information on input. We add more information, so we get a new input expression, and we get new computation. So we have more computation going on. So more computation, the system activates again and starts running. So, but then again it stops, and we have a partial termination. okay, again. And we can keep doing this forever. We can keep extending the string. But each time we add some information, there's some computation, and the result stops again. So we have partial terminations. Something times, this is called a resting point. So in theory of programming languages, where the system kind of rests, okay? You give it 1, 2, 3, it computes, and it's over, it's done. Resting point. But I like to call it partial termination because it actually terminates, but not completely, only temporarily, okay? It's like a temporary termination. So each step of this, Church-Rosser still applies, okay? So this is one way where we're going beyond Church-Rosser. We have this partial termination. See? To take a step back, I want to use the power of Church-Rosser in as much a way as possible. But just computing one expression and giving one result, it's not enough in real applications, because I'm doing more, okay? So I'm going to use this as kind of a building block and do more, use it to do more powerful forms of computation which are still confluent, okay? So the first one here is partial termination, but that's not the only way I'm extending lambda calculus. There's another extension. I will call this one logical equivalence, so you'll see why. Because the lambda calculus does not have singular assignment variables, has no data flow variables. Okay? It has only functions, values, and application of functions. Here we have these data flow variables. Okay? So for example, I have inputs x and y, and I'm doing x plus y. So the function is addition. Okay, I'm doing an addition here. X plus y, I'm doing x plus y. This is my function. That's the output. But x and y can be unbound. But in Church-Rosser, that doesn't exist. Unbound variables are not existing here. So how do I take care of these unbound variables? Also the streams. If I have 1, 2, 3, s, this gives me 1, 4, 9, let's say t. This s is an unbound variable. If I bound s to 4 bar s prime, then I'm extending the stream, and t will get bound to 16. So I have these unbound variables in there. But Church-Rosser does not have unbound variables. So what do I do? Okay. Well, we can take care of the unbound variables. So the way we handle unbound variables is that we can look at the possible values. We look at possible bindings of the unbound variables. Each time we bind it, we get a value, and Church-Rosser applies. So if we have 3 plus 4, if x is 3 and y is 4, then the Church-Rosser applies, if we have values. But we can also have 4 and 6, and we get 4 plus 6. So there's many possible ways to bind them. So we actually look at all the possible bindings. Okay? So we have the input with unbound variables. Okay? And we have the output also has unbound variables. Okay? So let me make a group here. So we can say, so in order to apply Church-Rosser, two outputs are the same. So let me call these outputs output C1, output C2. If they have the same variables, and for each variable, the possible values are the same. So this is actually kind of a technical thing. Let me explain it with an example. Let me show you a simple example of this. So here's an example. So let's say I have two variables, x and y. Okay? And then I do computation, and I will bind x is equal to 1, and I will bind y is equal to x. Okay? This is one reduction sequence. But I can also do another computation. Okay? I can say, for example, y is equal to 1, and x is equal to y, for example. Okay? Or maybe if I do another computation, I get x equal 1, y equal 1. So the result is actually bound variables here. Okay? But there's different possibilities. But in fact, they're all going to be the same. So what does it mean? Actually, you can see this in terms of logic. These are actually logical relations. X is 1 and y equal x. So these are logical relations. Right? If I say x equal y, then I'm putting a relationship between x and y. I'm saying x and y are the same. But I'm not saying what they are. They can be many different things. Okay? But then I have x equal 1. So y is also equal to 1. Okay? So this one, so the values, the possible values, for x has to be 1, and y has to be 1. So they're all going to be the same values. So even if the variables are bound in different ways, they give the same values. So this is actually a logical condition in terms of first order logic. But I'm not going to give you a course on logic here. So this is actually can be defined in terms of logic. So the result of the program here is a set of bindings, which I can call it a logical relation, but it's actually a constraint. C1, C2, C3. These are logical relations, okay? But all of them give the same result. So basically I can say if execution gives C1 with one reduction order, and C2 with another reduction order, then for all variables, for all unbound variables in for all variables x in C1 and C2, I have that the values that are possible for x in C1 is equal to the values that are possible for C2. Okay? Okay, I don't want to give a course on logic here, but I just want to tell you that the result is actually the same. Even if the variables are bound in different orders, the possible values for the variables are the same. Here, that both x and y will always be equal to 1. Okay? So basically what that means, it doesn't matter if the result has unbound variables. So even with unbound variables, the results are the same. Okay. Result is the same. Okay, I don't want to say more because otherwise I would have to give a of course on logic. But basically, the idea is that the result here, the two results are going to be the same. So if I have an initial expression that might have data flow variables in there, and then I do some reductions here, and I get a result here. This is a result. And I do maybe other reductions from the main expression. So because I have concurrency, there's many possible reductions. This is a result, this is a result. Then these two are actually going to be logically equivalent. They're not exactly the same, but the variables in there are going to have the same values. So the variables maybe are not bound exactly in the same way in there, but if you look at the possible values of the variables, they're going to be the same. Okay? So because of that, we can still get a confluent result. Okay? Okay, and now we can make a definition of declarative concurrency. So we can say a concurrent program is declarative if the following conditions hold. So we have a declarative all executions with the same inputs either have two quotes. Either they all do not terminate, because you still have infinite loops, or they all reach partial termination and the results are logically equivalent. Okay? So with this definition, we kind of capture this way we extend the Church-Strasser. So we take an input, we run it, either it goes into an infinite loop, it's possible. But if one execution goes into an infinite loop, they will all go in infinite loop. It's not possible for one of them to go into an infinite loop and another one to terminate. So either they all do not terminate, or they will all reach a partial termination. They all end, and the results are logically equivalent. Okay? So we get back this situation where the results are all the same. Okay? So there's a termination, and they're logically equivalent. Okay? So that's how we can define declarative concurrency. There's also a third idea that we need to talk about, that are declarative. Let's say we have a large application. With many is huge code. It's not all declarative. Some of it is not declarative. And there's a piece in here that's declarative, okay? And then there's a piece that is not declarative. And so there's different parts in here. Now, let's take a look at this part here. There's a piece declarative and not declarative. Well, this not declarative part is kind of a pain, because it's like contaminating everything. It makes everything non-declarative. Now, if you have a big program, and part of it is non-deterministic, then the whole thing is non-deterministic, okay? If inside here, this might be non-deterministic, maybe there's a timer or some weird thing, interactions coming in here, and it's not declarative, because sometimes it gives different results. Well, it contaminates the whole program. So that's kind of a pain, because we actually want to use declarative as much as possible. So what can we do? Even a small non-deterministic piece inside will contaminate everything. So, but we want our program to be declarative. So how do we fix this? Well, what can we do with this? Well, we can try to hide the non-determinism. So we can try to hide or encapsulate the non-determinism, so that from the outside it still looks declarative. So we can make it so that this box from the outside, it still looks declarative. It still looks like this. They all give the same result, logically equivalent, even though inside they have this non-deterministic bit. Okay? So from the outside, it's declarative. So the idea is that we have a big program then, with lots of declarative pieces. And here's a non-declarative piece. And maybe it's non-deterministic. We can actually encapsulate it. So it looks declarative from the outside. Basically, we capture the non-deterministic result, and we make sure it looks deterministic from the outside. So then the whole program is declarative again, even though there's a piece inside that's non-declarative. If we don't do this, then declarative doesn't really help, because it contaminates. The non-declarative was like a virus. It contaminates everything. Okay? So, for example, to show you an example of this, so let's say we have an error. We divide by 0. Or we have square root of a negative number, which doesn't exist in real numbers. But we divide by 0. This is an error. Error is not declarative, because the program has undefined result. We cannot give a result for this. So the way to do this then is to catch the error and fix it somehow. Fix it and return a reasonable result. So here we can do things like exceptions handling. Okay? So the basic idea is to put a box around the errors so that from the outside it still looks clear. Okay? Okay, so that basically, that's all I want to say from the theory point of view. So from theory point of view, everything is built on Church-Rosser. So let me just summarize that. All the advantage come from this, and it's a major result. In fact, all programming languages are built on top of lambda calculus and with extensions. But the lambda calculus only does this. It has an expression and you reduce. It's one computation. So the idea is we want to use the power of this as much as possible, okay, in real application. So we have our declarative models. So we extend Church-Rosser with partial termination and logical equivalence. And this lets us have really powerful declarative programs. You've seen it, lazy, concurrent, that do all kinds of smart things, okay? And then the final point is, we still need non-declarative things sometimes, either non-deterministic or programs with memory inside or weird stuff going on, errors. There might be a crash going on in there. And so we need to encapsulate. So this is the final idea. We can encapsulate the non-declarative parts so that the program looks as much declarative as possible. And if we do that, then we can actually get very reliable, very powerful programs that take advantage of the declarative systems. So let me give an example of this. So MapReduce is a nice example of this. So MapReduce is a functional computation. You have an enormous list of input list data. This can be gigabytes, huge. We do some functional computation and we get an output list. Okay? I'm not going to say exactly what it does, but it's purely functional. You do a map and you do a reduce. A reduce is like a fold, it's the same. And this is what Google used in the 1990s to calculate their page rank thing. Okay? So the way they did that, they did a distributed implementation of this. So let me show you how it works, and then I'll show you how they make it completely declarative. So this is functional, okay? This is declarative. So we have here a system, a distributed system, with many computing nodes, many computers, basically a cloud, a data center. So Google actually invented this concept in the 1990s because the page rank computation is huge. Okay, this data is basically all the matrix explaining the connections between all websites. And even in the 1990s, there were hundreds of millions of websites, so it was huge. Okay, so you had to make a parallel computation. So we have here a bunch of computers here. These are all computing nodes, and they're all connected in a network, okay? They're all networked computing nodes. And they're all doing this computation. And we can have hundreds or thousands of these, okay? Of nodes, because this is a huge data. And even today, this is terabytes or petabytes. So 10 to the 12, 10 to the 15. It's huge. So they're still doing this stuff today. Yeah? And many people are now using cloud. So we have this huge computation. But it's simple because it's still functional. It's declarative. That means if part of the computation crashes, if I have f of x, so x is the input, is a huge data, and I compute f of x, okay, and it crashes. The system crashes. Oof, pain. No problem. We just re-execute f of x. And we know the result will be the same. You can tell, well, that's pretty obvious. That's only true because it's declarative, huh? And this will give the same result. Why? Because the input is the same and the function is the same, because it's declarative. So this is a pure declarative computation. And in this distributed system, we have thousands of nodes. Nodes can crash. That's a pain. Crash is not declarative, huh? So how do we keep the whole thing running even if node crashes? Well, we use the property of declarative program, which means that if we execute the same function again with the same arguments, it gives the same result. Okay? Church-Rasser, the same input gives the same result, and it doesn't matter how we execute even. So this one We re-execute f, but it can be executing in a different computer in a different way. We don't care. The result is the same. So if this guy crashes, basically we put the computation, we move it, so we detect the crash, we move the f of x computation to another node, and it changes a lot, the communication and so on, but it's encapsulated, okay? And the rest of the system will not even see the error. Which means that the MapReduce will work even if the nodes are crashing all the time. And it's very easy to implement because of the fact that it's declarative, okay? So this is a really nice example of the advantage of declarative. And in a large-scale computation like this, running on thousands of computers, that's the only thing that works, okay? Non-declarative is hard already on one computer. If you want to do non-declarative on thousands of computers, you're dead. All these big computations in cloud, they're declarative. And the reason is not because all the Google people are mathematicians or theoreticians and they like theory. No, the reason is because this is the only one that works and that you can debug and that you can test. Okay? So, and all the cloud tools today are descendants of MapReduce. Okay, MapReduce is the first one. I like to mention it because it's a simple one. Today you have a huge set of cloud tools. And if you follow the course on cloud computing, you will see many of them. But they all are inheriting descendants of MapReduce. And they will all be highly declarative. Okay? And whenever they try to do something non-declarative, it's very hard. Sometimes they try, because the tendency is strong to do that. But it's very hard to build it so it works. So all these large tools are mostly declarative, and they will, whenever there's a crash, a non-declarative thing, they will encapsulate it and make it declarative again. Okay? So from the outside, it looks declarative. So from the outside, it looks like this. Okay? That's very important. And then the rest of the system doesn't have to worry, and you can keep running it as if it were declarative. Okay? So Cloud Tool is maybe the best example of why all of this stuff is important. Okay? Cloud big data analytics is now running a large part of society. Companies are based on these computations today in 2020. When Google started, it was only Google. And no one had data centers in the 1990s except for Google. Okay? And then you had Amazon, which came along as well, and a few companies like that, Facebook, they also needed this. But this was 20 years ago, okay, where they invented this. So it's kind of the victory of declarative programming in a sense, because in the 1990s, people didn't really believe that declarative programming was so important. But now, today, everybody is doing it. Okay? So what I'm telling you in this course is not just because I'm a theoretician and I love theorems, okay? Although I do like good theorems. It's because it's really practical and it works. Okay? So that kind of gives you a little bit of theory, but also an example to show the importance of the declaration. Okay, so now I'll make a small break. After the break, we go back down from this theoretical heights, and I'll show some more practical algorithms, very smart algorithms. So we do like algorithm design, okay? Like in the course of algorithm design that you followed, we're going to have a course on algorithm design. But first, I'll make a small break. On va faire une petite pause. Okay, so let me start again. So I'm going to do some algorithm design. I'm going to do some coding now that using some of the concepts we've seen. So the first thing I want to show you to introduce the ideas is a concept of a difference list. So a difference list is like a list. So remember we have lists. So we have a list. So here's a list. 1, 2, 3. And you can write it like this. 1 bar, 2 bar, 3 bar. Real? So let me write it like this. So we know lists. Lists are values. Well, a difference list is a representation of lists of a list as two lists. So it's basically as the difference of two lists. So this list 1, 2, 3 nil, we can represent it as a difference list. We can represent it as two lists as the difference of two lists. So for example, 1, 2, 3, 4, and the list 4. So 1, 2, 3, 4 nil, and 4 nil. So these two lists are just lists, but the second list is actually inside the first one. And if we take the difference between the two, we basically remove the second list from the first one, we get the list 1, 2, 3. Okay? So this is another representation of 1, 2, 3. Okay? So that's pretty simple, right? I represent the list of two lists. So why is that a good idea? Well, because the two list, the second list, does not actually have to be a bound variable. We can also represent it like this. 1, 2, 3, x, and x, where x is unbound. So I have 1, 2, 3, x, where x is unbound. And here we have the second list is unbound. So we don't know what it is yet. Could be anything as when we bind x. But the same difference, we can make the same difference because it's the same variable, x and x. That means this also represents the list 1, 2, 3 nil. So why is this an interesting idea? Why is this a smart idea to represent the list like this with an unbound tail and then a second variable? Because it's still the same list 1, 2, 3. It's just a different representation. Okay? So a difference list is just a representation of a list. Why is this a good idea? Well, let's say we have the list 1, 2, 3 as a difference list. And we have another list, 4, 5, 6 as a difference list. So we have two difference lists here. We have L1 and L2. So L1 is basically the same list as 1, 2, 3. Yeah? L2 is 4, 5, 6. Okay, well, let's say we want to append L1 and L2. Okay, we can write like this. We can do append 1, 2, 3, 4, 5, 6. And this returns 1, 2, 3, 4, 5, 6. Okay, fine. But we can also do the append on the difference list representation. So we can also do append. We can have the L1 as a difference list, L2 as a difference list, and we do the append, and the result, let's call it L, as a difference list. So how can we compute L, the append of L1 and L2, as a difference list? It's constant time. If we say, if I bind x to 4, 5, 6, y, then I will immediately do the append. If I do x is equal to 4, 5, 6, y, then L will be the difference list of the result. Then L is equal to this. L is 1, 2, 3, 4, 5, 6, Y. So, and if I combine it with Y, I get the append. So append is constant time. Now that's very nice, okay? I can append two lists in constant time if I represent them as difference lists. Now that's a real advantage, because if L1 is a big list, the usual append function takes order n, the length of L1. But if I represent it as a difference list, I can do the append in constant time. That's a really nice trick, yeah? So let me show you a program that does that. I'll show you how it works in practice. It's actually very easy to use this. Of course, there's a limitation, huh? I can only do the append once. That's the limitation. I can append L1 to something, but if I later on want to append L1 to something else, then I cannot use the differences trick anymore. It only works once. So the magic only works once. But in many programs, that's okay. Because usually when you build a list, you will construct a list from small lists. So you will only need to build the list once. Okay? So usually that's okay. So let me now give an example code, a program that does this. So let me go to the screen here. Okay, so let me now give an example of this. Let me write a flatten function, okay? Where flatten will take a list that might have lists and returns the list which has all the internal lists brought up like this, okay? So let me write a simple flatten function, okay? So I write it in the normal way, and then I'll show you how easy it is to write it with difference lists. Okay, so here's the regular flatten. Okay, so I will define flatten XS, and now I do a standard case. Nil, da, 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 da. Then I have X bar XR, and X is a list. Okay, and the final one is when it's not a list. Okay? This is a standard flatten, right? Simple kind of a function. So, how do we do it? Well, if XS is nil, then it's nil. If it's X bar XR, and X is not a list here, then it's going to be X followed by flatten of XR. But the middle one is where you really have to do, it's really a flatten, huh? Because X is a list in the middle one, so I have to do this. X, flatten X, because X could be nested as far as you want them. So this is a flatten. You see how it works? So in the middle case, X and XR are both lists, but in the flatten they can be nested as deep as you want. That means you have to call flatten recursively twice. Okay, on X and XR. And those two have to be combined. So I append them. Okay, fine. And now I can do something like this. Let me take this one. Okay, 1, 2, 3, 4, 5. It works fine. So that's a nice definition, right? Well, I'm kind of annoyed on this definition because it has this append call. And whenever I see append, I don't like append because it's like a overhead thing, okay? I have to copy all the list, the first one. So let me say, well, let me try and see if I can write it using a difference list. That's actually very easy. So the way I do it, let me see what's the simplest way. Let me write a new version of flatten with result as a difference list. Okay. So a difference list represents a list as two lists. Okay. Which means the result is going to be two arguments. Okay. The result is not just one list, it's going to be two lists. So I'm going to do it as a procedure because I actually will have two outputs. So the difference list is two arguments. So let me define it as a procedure to make it simple. But it's still doing just flatten. Let me call it D flatten. XS. And now I have the difference list here. So let me give these two lists a name. Let me give these ones a name. Let me call this one S and this one E, start and end. Okay. Start is the beginning of the list and end is the end. So the two arguments, S and E. And now the code is going to be almost the same. Okay, like that. I have X bar, so X bar XR, and then is list X, and I have the final one. And then okay, so the structure looks the same as before. But the code is going to be a little bit different. So first of all, when X is nil, well, what is the result? Well, in the original program, the result was nil. But nil is an empty list. So how do you represent the empty list as a difference list? So if I have an empty list, I'm going to write on the board, but okay. As a nil, how do I represent it as a difference list? Well, the first and the second parts, they just have to be the same. So S is equal to E. This represents an empty list as a difference list. Okay. Fine. What about now this one, where I have to do the append of the two flattens? Well, let me do the two flatten calls, and then I do the append. D flatten X, and then the result is a difference list. But I want to connect, so SE, so the result is the first part of the S. So let me make an S here. Let me call the second argument M. X, R, M, E, and M I have to declare it. So you see what I'm doing here? SM is the flatten of X, and ME is the flatten of XR. Those are two different lists. And the M is the same, which means basically I've bound the two different lists together. I've appended them. So SE is actually going to be the append. You can actually kind of, I like to write it this way as a picture. So we have S, E. So we have in here, so we have SE is the append of SM and ME. Okay? You can kind of see it like that. SE is a difference list, SM is a difference list, and ME is a difference list. So SE is the append of SM and ME because the two M's are the same. Okay? And now the final one, I have to add X to a difference list. So how does that work? Well, I have a difference list with one element. So what is a difference list with one element? It's the element, bar, and then the second part. So S is going to be equal to X bar E. So SE here is a difference list with one element. Huh? So the difference list is, so I have X bar E and E, okay? The difference list, the two parts of the difference list are X bar E, which is S, and E. So that represents just X, okay? So here we now have a flatten, a deflatten, which does the same thing as before, only no append. Poof, the append has disappeared, okay? It's a nice magic trick, right? Let me show you that it works first. We can make it work. Okay, let me do that. Because it's a procedure, we have to call it like a procedure. So we have 1, 2, the same argument as before, 5. The result is S nil. So this is a difference list, SE. But no one is preventing me but already binding the E there. If I put an E there instead of a nil, then I can bind it to other things later on. But if I want it to turn into a normal list, it's not a difference list, I just make the second one equal nil. Okay. I have a mistake here. What did I do as a mistake? Oh. 135. Oh, I think I made a mistake somewhere. What did I do wrong here?
Vous faites pas flatten dans le dernier cas.
Sorry?
Dans le dernier cas, vous faites pas flatten sur XR. En dessous.
J'ai pas compris.
Quand X n'est pas une liste, vous faites S est égal à XE, du coup c'est nil, et vous laissez XE sur le côté.
Oui, merci. So the error is that I actually have to do a flatten at the very end. Huh? Here I have X, flatten XR, and here I'm not doing it anymore. Huh? So X is not, so here, so there's a bug here. I didn't actually copy this one right. I have to do a recursive call here. Thank you. This guy's smart. Okay, so I have to do a flatten here. I have to do a deflatten of XR. Okay, and this, the X has to be put on the front of that, okay? So X, M, and I have to do like this, huh? Sorry, the X has to be put in the front, not at the end. This. Right? So here I've put X in the front, S is X bar M, and then the difference list ME is the result. So this looks like it's correct, huh? Right? Isn't it? Okay. So my program had a bug. Let me write it again. Yes. 1, 2, 3, 4. Okay. Thank you for fixing the bug. So you see, this is a very nice technique. And it's extremely efficient. It's like linked list, okay? It's like linked list in Java, only it's still declarative. So we keep still all the advantages of declarative programming, but we can do like linked list, where we can connect the two things just by making one change, which is the binding of the single binding. Binding of the second element. This is actually a very useful technique, and most programs that use lists can be written with difference lists, okay? I think in the book there is an example of merge sort using difference lists. So you need to represent the list as two things. That's basically, and then make sure you do it right. You see, but it's not really very complicated, huh? Okay? So that's a difference list. Let me now give a general statement on that. Okay, here's a general rule. Let me give an interesting general rule because this shows you an example of it, which is called the 0-1 infinity rule. So let me go back to the screen. Okay, the other screen. So let me now show you just a simple rule, because it's nice to have little rules that help you build good programs. Okay? So this is the 0-1 infinity rule. Whenever you have something that's possible, so whenever you have an operation in a program that's possible or not, there should be three possibilities. It's either possible 0 times, which means it's not possible. It's possible infinite times, like when you update a variable in Java. You can do it as many times as you want. Okay? This is like updating a variable. Huh? There's no limitation. But then there's this very interesting case in the middle. The third possibility is that it should be only possible once. And then it's over. So 0 times, this is like the notion of a value. Okay? It's a constant. You cannot change it. So updating a constant is not possible. Whereas infinite times is like mutable state, a variable that you can assign as many times as you want. But the 1 time is like a data flow variable, a single assignment. So the difference list is using this. So what we can see is that doing once gets part of the advantage of mutable state, and it keeps the advantages of declarative. Okay? So let me write that down in a different color. So the 1 time case, it gets part of the advantage of mutable state. You can assign it, but only once. And it keeps all the advantage of declarative programming. So it's a very nice intermediate point. It's allowed, you can assign it, but only once. If you want to assign twice, then it doesn't work anymore. Only once. But you still keep all the advantages of declarative programming, which is very good. So this is a very interesting intermediate point. Okay? So that's the 0-1 rule. And difference list is an example of this, because you can append them once, but not more. You can see it's already very useful. Now let me show you another example, more sophisticated example, using queues. Make some space here. Another example of algorithm design using queues. So what is a queue? Well, a queue is basically like a list, but it has a front and a back. Okay? Okay? You can put elements in on one side, and you can delete elements on the other side. Basically, that's it done. You put elements in the queue, and the first element that comes out, it was the first one that got put in. So how can we implement the queues? In declarative programming, in declarative paradigm. Well, the naive way of implementing a queue is that the queue is a list. Okay? I represent that as a list. Okay? So I start with an empty queue, nil. I insert 1. I get the list 1 bar nil. I insert 2. I get 2, 1, nil, for example. I insert 3. I get 3, 2, 1, nil. Okay, I insert, so the insert is very fast here. I just put it in the beginning. But if I want to delete, I have 3, 2, 1, nil. I can delete an element, and it has to give me 1. It has to be the other side from the insert. It's 1, and then I have 3, 2, nil, and then I delete 2, 3, nil, etc. So how fast is this implementation? Well, the insert operation is constant time, O1. But the delete operation is O(n). Because in the declarative model, the only way to access the last element of a list is to traverse the whole list, and then I have to update the list, and I have to remove the last element. The only way to do that in the declarative model is to create a whole new list without the last element. So it's kind of expensive. Okay? Okay. Now, let's try to do better than this. We want to do smarter than this. So the naive queue is not very efficient. Of course, we can implement lists in Java using linked list, and then it's O1 and O1. But we're not declarative anymore. We want to stay declarative. Okay? So we want to do a declarative list. So a better queue. So we want to do a better queue. So let me show you a better one. Let me show you an amortized constant time queue. An amortized constant time. So what does it mean, amortized? Have you seen that already in a course? You know what it means? Well, in this case, I'll just say, if I do n operations, they will take order n time. So I do n operations, which can be insert or delete. They take, altogether, they will take order n. That means on average, an insert or delete will be constant time. But it might be that a single insert or a single delete is expensive. It might be. But if I over n operations, it will be cheaper, constant time. Okay, so I will show you that, an amortized constant time queue, and then I will show you a worst case constant time queue. It's declarative. So worst case is very good. That means each insert and each delete will be constant time. Whereas in the amortized, I will only have the constant time on average. Okay? If I do n operations, the total would be order n. Whereas here, each operation, single operation, will be order 1 for insert and delete. So the amortized queue is implemented in strict functional programming. So no data flow variables needed. Whereas the worst case, I will use data flow variables. Okay? So you see that adding data flow variables gives me a better result. So maybe amortized is good enough, or maybe not. Okay? So let me show you now the amortized one. Amortized constant time Q. This is actually already a kind of clever algorithm. Huh? So I have new Q, which returns an empty Q. So I will represent the Q as a tuple of two lists. Okay. And I have an extra helper function called check. Okay. Case Q of nil R, then reverse R nil, else Q. Okay, so this, I have a little helper function here called check. It looks at the Q, and if it's the second element of the list is R, and if the first one is nil, then it will basically make the second element nil and put reverse of it in the first. Okay. So basically, I represent the Q in two parts. So, okay, but let me first show you, and then I'll explain how the magic works. So I insert now an element in a Q. Okay. So I have Q FR, then check Q FX R. Okay, that's an insert, the delete. QX, case Q of QFR, then check. Sorry, no, let me do it differently. F is equal to XF1, and check F1 R, and I also have an empty, it is empty, but let me just do this. Insert and delete. Okay, so I think this is correct. So now let me define it. This is good, compiled everything. So now I can create a Q. So Q is equal to, I insert. So I have a new Q. I'm going to first insert 1, then 2, then 3. Okay. Okay, so this is the result. Now I can delete. So I do a delete. So that would mean Q1 is delete. Q x1 browse x1. Okay, so this does the right thing. It deletes 1. Okay, I insert 1, 2, 3, and I delete, and it returns the first thing that was inserted. And it's amortized efficient. So how does it work? So how does the magic work? So this implementation is actually going to be amortized constant time. Okay? So how does it work? Do you have an idea how it works? Let me explain how it works. So let me go back to the board. So how does that one give me an amortized constant time? Well, there's this magic check function. So when I represent the Q, so the Q is represented here as Q of FR, with F and R, it's 2 lists. In fact, the content of the Q is a combination of both of these. Huh? It's append F reverse R. Okay? So the actual content of the Q is a combination of these two. It's F plus the reverse of R. That means when I put elements in the Q, it's very easy. I just have to stick them in front of R. Okay? And when I take elements out of the Q, it's very easy. I just have to take them from the front of the F. You see that? So insert, I just have to put in front of R, because that's the very end of the Q. And to delete, I get from front of F. So these are both constant time. Well, if R and F are non-empty. Okay. So insert is always constant time, because I can always do that. But the delete will only work if F is non-empty. See that? But I would like F to be non-empty. So to make this constant time, F has to be non-empty. How do I make F non-empty? Well, if it's empty, I take the reverse of R and I put it as the new F. Okay? See how it works? Let me show the code again. So in the delete function here, okay, actually I'm removing elements, but there's this check. So look what the check does here. The check is actually what makes the F non-empty. If the F is empty, then the check function will replace it by the reverse of R, and it will make R empty. So, but that's not always necessary. It's only necessary that F is non-empty. So you see the amortized trick here is that I take elements out of F, and when F is empty, I put the R in there. So sometimes I have to do reverse, but most of the time I don't. So this is amortized constant time. And it's purely strict functional programming. See that? It's a nice trick, huh? No, isn't it? Okay. So now let me show you even better one. A worst case constant time, Q. So this one is amortized, but it's strict function, which means that I have no data flow variables here. Huh? But if I add data flow variables, I can do even better. I can do worst case constant time, just as good as as in Java. Okay, but with the advantage that it's purely declarative. Okay, so let me show you now. Let me do the worst case constant time q. Okay. Well, again, let me have my new q function. This time I represent the q as a kind of difference list. I represent it like this. XX represents the empty q. Okay? Empty q. But I have to add a third thing, 0, because otherwise I don't know that it's empty or not. Okay? Because they're unbound variables, and you can't really check unbound variables. So I have to put a third, I have to put the 0 there. So this is representing as kind of a difference list. So I do insert qx. So here's the insert. So NSE. Okay. And basically, I will put it at the end. So this is a difference list, SE. So I have to make a new difference list where X is at the end. So that's actually very easy. Okay, so adding an element to the end of an if difference list. N plus 1, SE1. So here we go. So basically, SE is a difference list, but I have to put X at the end. So I need a new E, okay? So I have E is equal to X bar E1. So I'm basically appending X to the end. And the new difference list is SE1, which has X at the end. And I can do delete. QNSE. Here I have to remove an element from the beginning. So SE again is a difference list, but I have to remove an element from the beginning of the difference list, so from S. Okay? So I need an S1, so I have to do S is equal to X bar S1, and then the new difference list is N minus 1, S1. See this nice, the nice trick that I'm doing here? So SE is a difference list, but I have to remove an element from the side S. So I remove it, S is equal to S bar S1. So S1 is like one down, one farther up. So the new difference list will be S1E. Okay? Notice both insert and delete are constant time here because of the difference list that I'm using in both. Okay, and I think I can use it exactly the same as before. So the API. So here's the original one, the amortized constant with new insert delete. Okay. What's going on here? Nothing. Should be fine, huh? Bad network quality. That's why I'm making a video. Okay, so the API is the same. So this one should work exactly the same as before. So let me take this code here, and we'll call it in the bottom case. So let me compile this one. Let me now insert 3 elements. Notice the result is looking a little bit weird. 1, 2, 3, underscore, underscore. That's actually a difference list. Huh? And now I can delete the first element. This will give me, should give me a 1 if everything is fine. 1. So the result is exactly the same as before. So the API is exactly the same as before. So the worst case constant time Q and the amortized have exactly the same API. Only the worst case is always order 1, and it's using data flow variables. And the amortized one, the delete sometimes is order n, but it's amortized constant time, but there's no data flow variables. So here you can see directly a complexity advantage of these data flow variables. We're going from order n, amortized, but still, if I do delete, sometimes it's order n, but in the second one, guaranteed constant time. So far I have not used laziness. I can actually use laziness to make even better algorithms. Okay. But I won't do it this time, but I'll do it next time. But I'll just say, so laziness can make even improved versions of this. So how can you get better than worst case constant time? Well, that's as good as you can get, right? Actually, there's another improvement you can make. You can make the data structure persistent instead of ephemeral. So let me explain. So I have the notion of ephemeral versus persistent data structure. So an ephemeral data structure means you can only have one version at the same time. So if I have a queue and I do an insert, I get another queue and I can do another insert. But at any time, I only have one version. There's only one version of the queue. Persistent actually goes beyond that. It's a very interesting property. If I take Q1 and I do an insert, I get Q2. But if I take Q1 and I do another insert, a different insert, like here I insert 1, here I insert 2, I get Q2 prime. This means that Q1 is I insert 1 in Q1 and I go like this, or I do Q in 2 in Q1 and I do like this. This doesn't work. This doesn't work for the constant time Q, because I can only do one append in the difference list. Okay? So to make it persistent and constant time, so to do persistence, I will actually need to do lazy evaluation. So neither of these actually work in persistent. Both of these are basically ephemeral. Both of them are ephemeral because only one version can exist at the same time. It doesn't work for two versions. In order to make it persistent, you can use lazy evaluation, and it gives you persistent data structure. That's a very powerful thing. It means you can use the data structure and like duplicate the data structure as many times as you want, and it's still constant time. Okay? So most data structures that you implement are going to be ephemeral. So a queue in Java will be ephemeral. Because you can only have one version. If I have a queue, which is an object with attributes, and I update it, that's only one version. I don't have two versions. So a queue in Java will be ephemeral, and these two queues are also ephemeral. So many data structures in real-world systems are going to be ephemeral. But if you want a persistent data structure, which means if you want to use your data structure in multiple versions, maybe you have two different users. Maybe you have like a collaborative editor, and one person wants to do changes to the document, and the other person does other changes to the document, and they have to diverge. Then the data structure has to be persistent. Then this technique will not work. But you can actually make it work with lazy. And that's more magic. But this magic I show next week. Okay? So let me stop here. So there were no questions this week. Maybe I was way too obscure. I hope not. But, so I stop here. If you have any questions, please ask. I will again put the video on YouTube. At this time, it's explained in the book. All of this stuff is in the book.